Alrighty, welcome back everyone. Congratulations on all being alive. I will say the same tomorrow after we've gone through 3 or more hours of statistical analysis. I'm serious. You think I was joking? But if you have trouble sleeping, I will resolve it. So
Who doesn't love the Martin Moffat?
Sure. Yeah. All those regressors and estimators. How can you have a bad feeling about those? All right, so what I'd like to do now is let's just imagine you've narrowed down on the exact task you want to do. You've narrowed down on what you want your subjects to do, which means you've translated your conceptual design into an actual task that you can have someone do in an MRI machine. You have your stimuli set, you have conditions A, B, baselines, all of that. Now there's an empirical question about how you're going to organize the events inside the MRI machine. And it turns out how you actually organize the events has quite a big impact on what happens, I guess on power, for example, and many other issues that are very important. So the most standard, traditional, vanilla, call it what you will, design is to do a block design. And this, came straight in from PET. This is exactly how you do it. Right? You'd inject something, and after a little while, you'd have somebody do a lot of task A, maybe seeing a bunch of faces. Then you'd have a big break, and then you'd restart. You'd acquire more data later when they were not seeing faces or something of that sort. A nice block design. In this case, maybe you might see face for 30 seconds, then nothing, and house, and then nothing, and face, et cetera, et cetera. Maybe in blocks, who knows, of 30 seconds on and off, something of that sort. The standard block design, it has a lot of upsides and some downsides. And I want to force you to think about what are the upsides and the downsides. Let me start by comparing this block design to so-called space mix trials, or you probably know them as a slow event-related design. Right? And the idea is that now instead of sort of putting nearby all these trials, often prevents you from doing certain things. And because of those things, it might be advantageous for you to actually have a trial, then a little break, then another trial, a little break, another trial, a little break. And I'll go sort of over some of these issues. Actually, sorry, let me just... Could see, there we go, okay, perfect. There we go. Alrighty, right, so you might choose to do this, and I will come back to why you might choose to do this. Just because it's a traditional or old, it doesn't mean it's any less good. In fact, it has a lot of, as I was saying, positives going for it. If you ever can, then this is probably one of your best designs. But if you can't, and there are many reasons, and I'll get into them, then you might do something more akin to this, right? Little condition break. The most, there are 2 things will strike you right off the bat. And one is that now you can, of course, intersperse, right, different conditions. So you can have condition A, B, A, B, B, A, B, etc., which you couldn't really do right up here. And I'll get back to these particular details in a moment on why you might want to choose an event-related design. And so the idea is that now instead of sort of getting an overall response for 30 seconds of doing, being hammered with task A, you can actually sort of get the individual response to every single trial. So maybe, who knows, I think in this experiment you were hearing words. So you hear one word and you get the full deflection, the full bold response elicited by that one stimulus, and then it returns to baseline, and then boom, the next one. And you can actually see right here, right, the response of this particular voxel. In fact, you can even average them and kind of get the average profile, right, of what happens upon hearing a linguistic stimulus. Now, of course, the question is, why on earth would you do this as opposed to block design? And there are many reasons. I just want to highlight sort of the most typical ones. But you might think of your own experimental design and think of why, right, in your design it was so optimal to do an event-related design as opposed to a block design. For one, and this is probably one of the most obvious ones, you can randomize the conditions or the events happening, right, which you can't with a block design, or at least With block design, you can't randomize individual occurrences. You can just randomize sets of occurrences, which might or might not be good. In particular, oftentimes having sort of block designs will create expectations or things like that that are problematic and that start meddling up with your task of interest. Right, so for example, imagine this is your timeline, and now you wanted to use block design, and maybe you scary picture, scary picture, scary picture, break, 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 non-scary picture, non-scary picture, non-scary picture, right, et cetera, et cetera. And of course, first of all, what's happening is extremely transparent. Your subjects are going to develop straight away strategies on how to cope with this. I mean, the simplest of all, if your subjects were really averse to the stimuli, what could your subject do? Close their eyes, right? As soon as they see the very first stimulus, oh my gosh, I'm in a scary block. I'll close my eyes and won't look at it. And I'll sort of wait a little bit until I feel I can open my eyes again and look at the beautiful pictures. So of course, right, these block designs might trigger all sorts of cognitive sets and things like that, which, as sort of we spoke about earlier, are going to be very hurtful to your analysis. So that's sort of one of the most basic ideas behind actually jittering these. Actually interspersing these rather than in blocks in single events. And now, of course, you might have, oh, scary, nice, scary, scary, nice. And you might even think that every time you're getting sort of a full response to each of these stimuli, which is much better. And in particular, you're really minimizing these expectations of strategy by just randomizing your stimuli and just submitting them to your participant in a completely random order that they cannot anticipate. Therefore, they cannot create strategies, expectations, and things like that. And I mean, if you've ever been a subject to an MRI study, to task-based fMRI study, you will know that when you're in there, you're really trying to figure out what's happening. You're coming up with all sorts of theories on how these stimuli reach you, and your subjects will do that. Right? Most universities, your vanilla undergrad is probably very clever and does great on GREs and is really trying to figure this out to show who's boss. So here's why you might want to use event-related designs. Another good idea is that it actually allows you to do things that you couldn't do with block designs. For example, you might classify post hoc what is condition A and what is condition B. Beautiful example now in '98 by Wagner and colleagues. And they showed a number of words and during scanning, one after the other, sort of in this slow event-related design. And your task as a subject was to, I believe, to report whether it's a physical object or not, right? Or something abstract or concrete noun, something of that sort. And you just see word after word and you say concrete, abstract, concrete, abstract. But the task was not sort of what they were interested in was not whether something is an abstract or concrete word, but they were interested in what does it take or what is different about things that you recall later on versus things that you don't recall later on. So what happened after the scanning is they would surprise the participant by saying, oh, I forgot. Could you just fill out this little questionnaire for me? And they had a recognition memory test, right? They'd show words and say, was this there? And they'd see if the participants, which words they would remember and which not. Now, you can analyze your data by taking all the words that were remembered and looking at the activations at encoding of those words versus all the words that were not remembered. And now you can try to see if you can tell something about what is different about words that spontaneously get recalled later on versus words that somehow faded, right? Their trace kind of faded out of your ear. So what they do after is they would take hits and compare those to the misses or the forgotten. Clearly, you do not know beforehand what is a hit and what is a miss. Therefore, there's no way that you can block hits or misses, right? You can only do this after. And if you had a sort of, you can't even create a block design, right, doing this. This would be another great reason to use a slow event-related design. Interestingly enough, you might see real differences when you look into the parahippocampal or fusiform gyri in terms of the remembered answers that tend to have sort of higher responses versus the forgotten ones that tend to have lower responses, right? So they wouldn't have been able to do this if it weren't for a slow event-related design. Interestingly enough, in areas that are not really memory tied, like visual cortex and motor cortex, there wasn't a significant difference between the remembered and forgotten, which if you were a reviewer, you would want to ask for. You just want to make sure that this is just not that subjects every now and then close their eyes and missed a word, and that's why they forgot it. They didn't recall it. Again, always have your reviewer cap on when you're coming up with your experiment. Think, if I were the reviewer, what would I say about this? Best way for you to sort of preempt some of the questions you could get. Alrighty. Now, sometimes, similarly to the previous experiment, really sometimes events can only the subjects can tell you when he or she is in condition A or condition B, right? And you can leverage this in very interesting ways. Frank Tong, a number of years ago, did a really cool experiment on binocular rivalry, and it went something like this. So you'd have a stimulus, and you can see there are, similarly to the stimulus I showed you earlier from my experiment, there are two things overlaid on top of each other, and participants would have those sort of fancy eyeglasses with a red and a green lens, which means that really what they would see is sometimes the stimulus would turn into face, and you'd really be focusing, your perception would be the face, and then it would flip, and now it's the house, and it would go back and forth, right? But the problem is that it happens spontaneously. You can't tell the subject in this design, in my design I could, but in this design, the subject will tell you, oh, now I'm seeing face, click. Now I'm seeing house, click. Now I'm seeing face, click. Now I'm seeing house, click. So in this case, only the subject can tell you when they are in condition A and when they're in condition B. The particularly clever thing that Frank did is that they recorded the timing that somebody spent in the face and then in the house and the switching, and then they replayed the stimuli really showing a face and really showing a house at exactly the same timing, what they call the yoked condition. So earlier you had the spontaneous switching and you saw face for a little while, house for a little while, and then they recorded when the subject said that things switched, and then they replayed a sequence but showing a real face and a real house. And then of course they'd look at whether these two things compare. So how different is it to have this attentional spontaneous shift versus an actual perceptual shift? Right. And it turns out actually you get similar activations, and sort of my study that I showed you earlier implies the same thing. So a very clever way of doing it. In fact, for example, in the yoked condition, when you're actually seeing a face and then flipping to a house, if you're seeing a house, let's say I'm flipping to a face, the fusiform suddenly gets really excited and the PPA gets all upset and sort of sad. And the same was true for vice versa, right? If you first see a face and switch to a house, the FFA now becomes sad and the PPA suddenly is all excited. Now this is when you're actually perceptually seeing differences. And what is interesting is that pretty much the same thing happened when it was your perception changing, but the stimuli was identical, right? So the stimulus you're seeing is the same ambiguous stimulus, but your own perception is shifting. You kind of see a very similar thing, right? For example, here from house to face, here's suddenly the FFA getting all excited and the PPA getting all depressed. So again, this is a condition in which a block design just couldn't work. Now, some things just cannot be blocked. And if you ever used an oddball paradigm, that cannot be blocked, right? So, if you're not familiar with them, it works something like this. You establish a standard and then you violate it, right? Standard, so here we go. You're my participant, yeah? The stimulus will appear there. Standard, 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 non-standard, standard. If you missed it, that was the oddball. Right? Now, I cannot create an oddball experiment unless I can create a context that has a standard. The oddball is the violation of a standard, so I need to be able to establish a standard to then violate it. Right? Of course, you cannot block oddballs. If you block oddballs, you're doing the opposite. Now your oddball is a standard, right? It doesn't work. So these are all types of designs that you can't do in a blocked way, right? Sorry, I'm gonna skip this one because I forgot to take it off from the slide. One important thing, and this gets often lost, it's not always obvious when the event of interest is, or rather, your decision upon when the event is happening can change profoundly what you're looking at. Here's an example. Be my participant for a second, all right? Keep your eyes on the screen. You're my participant, and this is the stimulus. You're inside the MRI machine. I'll go BBB while this happens. Right? So probably something happened in your mind. You've noticed there was something weird, right, happening. Now, if I place my event here, and model everything that happens from here to the end, what cognitive processes am I capturing? Obviously. Anything that has to do with language, right? But obviously, being a participant, you've noticed that there's something else going on, which is, of course, linguistic in nature, but really just happened here. So now, given the exact same stimulus, exact same experimental design, exact same everything, according to where I place my stimulus, the result of what I'm looking at is completely different. Yeah? The actual sort of what happens once you reach a violation in these kind of garden path sentences, and now suddenly you have to go back and recreate the whole tree in a different way, right, to make sense of what's happening. Not trivial, right, and can get lost, and you can end up with results that mean something completely different than what you originally intended. Now, let me spend 1 second talking about why not event-related designs. What's good about block designs, right? Well, for one, block designs are statistically more powerful. I mean, a block design, you're literally doing the fMRI equivalent of hammering someone, right, with a certain, I mean, you can hammer someone with checkerboards, with, I don't know, faces. I mean, you're really getting those parts of the brain as excited as they possibly could, given your stimulation, right? So if your design, if your task of interest is amenable to a block design, geez, from a statistical point of view, it's great. Not only, some psychological processes are really difficult to switch on and off, right? So a little while back, I was using quite a bit mental imagery for my experiments. And, you know, an experiment would be like something like, close your eyes, imagine playing tennis. Right? And then after a little while, say, okay, now stop. And then now restart, imagine playing tennis. Now stop. And it's kind of tough to start and stop quickly and at random this process. It's easier to sort of start it and then maintain it for a little while, and you really envision yourself on a tennis field and swinging your arms, something of that sort. It's tough to do short events of this imagery because it kind of takes a certain effort, and it takes time to develop it and to really engage in it. So I tried sort of shortening my blocks. It just wouldn't work. This really worked well with nice 30-second block design on and off. Right? And it didn't work any better at all the variations that I've tried in this experimental design. So in this case, a nice block design was the best I could do. Of course, you might keep in mind that excessively complicated designs are difficult for subjects. They have to remember, they get confused, and now just wonder how good is the data you're acquiring. Right? So these are all good reasons to stick with a block design if you could. Now, of course, there's an obvious there's an obvious pitfall of this kind of designs. If you just compare the number of events that are happening in your block versus your slow event related, it's clear that we are having many fewer events. Not only, we have way more junk time that we're paying very handsomely for, right? All these spaces in between add up to more than these 30 seconds on off periods. And by having fewer trials, we have less power, et cetera, et cetera. Our estimate is less work, blah, 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 blah. So the answer to that is what a lot of people do now. I feel it's a fairly conventional experimental design at this point, which is a rapid event-related design. You might call it a jittered design, and I'll get into that detail in a second. Now, the idea is that this is where we were, right? We stimulate someone, and then we wait for the full deflection of the hemodynamic response function. We wait for it to come back down, and then we hit the person again, and we get the deflection, et cetera, et cetera, et cetera. Now, instead, it goes more something like this. Here's the example of a jittered event-related design. Here's one event, then nothing, event, then another event right after it, then two events, then a tiny break, then another two, another break, another one, et cetera, et cetera. Right? And so now, by using this principle, I can actually jam pack in there way more stimuli than I could do, way more events that I could do with the slow event-related design. The problem, of course, is that now my hemodynamic response is overlapping across trials. Right? So now, for example, this one here is a nice response to one trial, but then this big thing here actually has two trials in it, and you know, I gotta be able to tease apart how much of this big thing comes from A and how much of it comes from B, et cetera. Right? Obviously, in the same length, which is the biggest positive, in the same length, I can pack way more trials. But as I was saying, the hemodynamic response now overlap, and that is problematic. So this, of course, begs the question, well, how do you tease apart right? How much of this big thing here comes from condition A versus condition B, right? The neighboring one. It turns out that really there's one key assumption that when you're doing this, you are making. And it's worth thinking about whether it's a reasonable assumption or not. And I will try to get into that detail in just a second. But really what you're saying is, look, my system is kind of, if you take a simple input out, let's just reduce what we're doing to a simple input out system. For example, neural activity fMRI signal. Just this simple system. Well, the system is linear if it really has two features at the same time, at least. One is scaling, and one is superposition. Right? And sort of superposition. Now, if a system, the beauty of this is that if a system is linear, then it's fairly easy to go back and say, oh, look, this much of that big curve came from task A, and this much came from trial 3 and trial 4. Right? You can tease those apart. Sort of in a sense, you can resolve this overlap, right, problem. Now, what does it mean that a system has scaling? Fairly intuitive. The greater a stimulation, the greater the response, right? So as simple as it could be. Probably familiar to all of you. Now, how many of you do fast jitter event related designs with overlapping responses? Okay, good. You know a question is about to is the bold response, does the bold response have a nice linear scaling? Of course, I wouldn't be asking if the answer were yes. And yet, all of you, guilty people, and myself, have published papers that assume that. And here's a beautiful demonstration. This is data from Bob Savoy. And this was just a visual stimulation. And you can see these three lines are the visual. The arrow indicates the onset of the stimulation. The HRF, the bold response to 34 milliseconds of stimulation, to 100 milliseconds, to 1 second. And it suffices to look at this to know the system is not scaling in a sort of nice, obvious linear fashion. It does scale, just not quite linearly. So, can we assume scaling, right? Is the right sort of question. Well, here's a beautiful experiment that really breaks it down. And the interesting thing is that they actually, if you look at this data, you can almost come up with an envelope where scaling might be a reasonable assumption to make. Now, this is Robson and colleagues, and they did something very ingenious. The stimuli were auditory tones, and you could either have one auditory tone, two auditory tones, four auditory tones, 8, 16, et cetera, et cetera. And then they did the following. They said, well, if the system is linear and scales linearly, I should be able to take the response to one tone, multiply it by 2, and approximate pretty well the response to 2 tones. Right? I should be able to take the response to 1, multiply it by 128 times, and get a reasonable approximation of a response to 128 tones. Right? Now, what you're seeing here, the bold line is the actual empirical response to 4 tones in a row, 8 tones in a row, 16 rounds in a tone, etc. And the light line is the inferred expected response on the basis of multiplying the response to 1 16 times, response to 1 32 times, response to 1 64 times. And it doesn't take a lot of stats to notice how far off we actually are when we do this. And sort of they do this in a number. So then you can take the response to 2, multiply it by 2, and you should be able to approximate 4. Multiplied by 4, you should be able to approximate response to 8. Multiplied by 8, you should be able to approximate response to 16, et cetera, et cetera. And it turns out that we still are quite a bit off. Right? By the time you get a response to 4, then your approximation is actually not that bad. But it's very clear at this point that the system does scale, but not linearly. Right? There's something happening that is preventing that is not making it linear. So can you assume scaling? Well, scaling, yes. Linear scaling, right? The second thing is superposition. And the idea is that if I have response to stimulus A, and I know the response to stimulus B, then I should be able to add them simply to get the response to A and then B when they're overlapping. Is this the case? So, in fact, if I see if this is my experimental design, but earlier I also had this, I should be able to take these two guys, subtract this guy, and be left with exactly this. Right? If the system is linear, then you should get this. Dale and Buckner bothered to look at this. They had as simple as interesting experimental design. Sometimes they had a single stimulation, visual stimulation. This is the one trial. Then they had sometimes two trials, one after a little bit after the other, and sometimes three trials, on, off, on, off, on, off. You can see it here, sort of one, then two with a little break in between, and then three each with a little break in between. If you take the response to one trial, there it is, and you see there are two lines. I think it's even trials and odd trials, so nothing that you need to worry about, the two lines. And now, let's look at the response to two. If indeed the system works out the way we expect it to be, we should be able to take the response to 2, subtract off the response to 1, and we should be left exactly with the response to the second one. And not only, because these two stimuli are exactly the same, what we should be left with an exact copy of this guy, just translating it in time, right? It should start around here, right? Once you subtract the one event from the two event. Turns out, not exactly the same. It turns out that the estimated second trial is a slight underestimate of the original trial. And then, of course, you can take the 3, subtract the 2, and then subtract the 1, right? Sorry, and then take what remains and subtract the 1 from what remains. And now you have, and now you should have the response to each one of those 3. And it turns out, you can see them right here, the response to the 3 events back to back are not the same. These are not perfectly overlapping lines, which they should be. So this tells you that actually, right, you cannot assume that if you have 2 overlapping things, you can perfectly recover each individual response. And the problem to you is that this creeps up in all sorts of ways. For example, let's say that you're interested in, you play words to a participant. What you're seeing up here is the response, the magnitude of the response to 10 words over a minute. Okay, if you play 10 words over a minute, which means each word is spaced, right, 6 seconds away from the previous one and the one after. For a given word, right, take word number 5 in there, the response to that one word is, on average, this big. If you have 15 words per minute, then the magnitude of the response of that one word is still kind of the same. But now put it in the context of 30 words per second. So now the spacing is only a couple seconds. Now the magnitude response to that same word is actually, right, is greatly decreasing. Now go to 1 hertz, and now the response is less than half, is almost, less than a third, just about a third of the response to that same word in the context of, right, few trials. So this is how this creeps into your effect. Right? Not only, you thought it was that simple. A different way of showing the exact same thing is when you're deciding how much spacing you want to put in between your trials. Here's the response to a single trial in black, and in red you're seeing the response to a second trial that happens 8 seconds later. Now do that 6 seconds later. Now do that 4 seconds later. Now do that 2 seconds later. Now do that 1 second later. Right? And you can see it's very nonlinear, the way in which it decreases. So this is the ways in which this problem creeps up in your experimental design and diminishes the effect that you are seeing. Not only, you'd think that this is the same across the brain. Turns out, not quite the case. What you're seeing here is if you had 2 trials back to back, how big is the second trial compared to the first one? Yeah, is the second trial identical to the first one? Then it would be 100% of it. Or is it half the intensity of the first one? That would be 50%. And what you're seeing on the x-axis is the distance from the occipital pole in visual cortex. So there you go. If you have trials that are 6 seconds apart, the second trial is just about 80% of the first one. Now put them 1 second apart, and the second trial on average is maybe just about 40% of it. And it looks kind of like a straight line. Distance from the occipital pole doesn't matter. Well, get further away into the fusiform gyrus, and now the story starts being very different, right? And as you go rostral, the effect actually worsens over time. So by the time you're, this far, this 50 millimeters away from the occipital pole, your second event that is 1 second away is getting penalized so much more than your second event that was only 25 millimeters away or 10 millimeters away or something like that. Right? So this is all the ways in which this becomes extremely problematic when you're looking into your data. Now, how do we actually, and given this, how do we tease apart trials? Well, really the secret is to shuffle things around. If you can shuffle things around, then you can at least recover each individual response. It still might suffer from these problems, but at least you can get a reasonable estimate out of it. Right, so the crucial point, in order to at least get something out, even if these effects will still remain, is that you really need to shuffle things as well as you can. Right? As I mentioned, I think in the previous slide set, counterbalancing is what people have used for quite a while, but it requires so many trials that it might be difficult to do. So most people that I see use full or pseudo randomization. One small important note: if you use full randomization, fantastic. Right? You're just randomizing everything for every subject, every run, everything is randomized, great. If you have enough trials, it should work out. But if you can't, let's say that you don't want to show the same stimulus twice back to back, and you start imposing these kind of constraints, so you do a constrained randomization or a pseudo randomization. My suggestion would be to create multiple pseudo randomizations. Right? For example, you might want to create 4 different pseudo randomizations, and then you might want to have some subjects do the first 4 this way, and other subjects do the same 4 randomizations but backwards, starting from the last trial to the first one. Right? You want to get clever in order to avoid discovering after the fact that a third of your subjects all had a certain order which you hadn't noticed, and now there's this big confound that you can't do anything about other than ditching those subjects and acquiring new ones, which is an expensive mistake to make. Right? Another good way of shuffling things around is really to just put randomization or jittering in between trials. Take the hemodynamic response to trials that are 16 seconds apart. This is what you would see, right? You would see each deflection, and then back to baseline, deflection, etc. Now put them 3 seconds apart. The actual variance that you're getting is just kind of this big increase and then a little squiggly line. So not much variance to tell how much of that big, right, how much goes into trial 1 and how much goes into the following trial 2 that is overlapping. Even worse, if you put stuff 1 second away, you really get this straight line. At this point, you can't tell which part of that line comes from any of your trials, really, and you're stuck. Now, do the exact same things, but just randomize the distance in between your trials. It doesn't matter much for those 16 seconds apart trials, but now you can see that you get all this variance, and this variance is what allows you to tell how much went into each part of that overlapping trial. Right? And it works very well even with 1 second fixation, with 1 second blanks in between. Very simple to do, just insert, right? Create a little jitter and insert it in between your trials. If you really want, you can you can fish that jitter from an exponential distribution, so that most of your jitters will be really tiny and then 1 or 2 will be pretty big. That works pretty well. Although in terms of power, I haven't seen it do any different from a Gaussian distribution, but it might save you some time. Another way of doing this is to actually insert every now and then a blank event. So task A, then blank, task B, task A right away, blank, task A, B, A, then blank, blank, task B, blank, task B, task A right away. You can sort of, by inserting these blanks in there, you're essentially doing the same as jittering, right? As long as you intersperse them randomly. Pretty much so you end up doing the same effect. So you really gotta do one of these, else your event-related design is not gonna work. Now, sometimes it is impossible to jitter events. You cannot shuffle around events. For example, you cannot shuffle around encoding with recalling. Right? You cannot recall before you've encoded. I mean, if you can, then you've proved precognition, which would win you a Nobel Prize. It'd be great. But short of that, it's tough, right? You're stuck. You always have to present, you will always have disorder happening in all trials. You'll always have your stimulus presented before you respond to it or before you recall it or before something. So in this case, a good way of doing is to have the retention interval be a jittered interval. So sort of your two events keep happening, encoding, recall, but the distance between the two keeps jittering. And by the same principle as the one I explained earlier, you will be able to create sort of an average response to the encoding and separate it from an average response to the recall. In fact, Russ Poldrak, I believe this slide here comes from Russ Poldrak. Finally, if you really want, you can mix these designs in clever ways. You can do what is called a nested design. For example, you might have blocks where you have, let's see, these are happy faces, then fearful faces, then happy faces, right? So the type of face you see happens in blocks, although within the blocks they're jittered, right? And then these are interspersed happy and sad faces, fearful faces, and these are interspersed happy and fearful faces. These are interspersed happy and fearful faces. And they are, as you can see here, they're jittered, right? They're randomly jittered. But then in blocks, you're attending to the gender of the face, or you're attending to the emotion. And then you can start looking at interaction. So you can combine these experimental designs to do clever things. Alrighty, good. Now, this was all easy, right? Come on, you must have encountered these things before. What is harder is to actually be confident that what you're doing truly is giving you the max bang for your buck. Look, these experiments, as Russ mentioned a moment ago, very expensive, right? And any mistake here will be a very costly mistake, right? Either to yourself, if you're sort of the one who found the money from some funding source, or to your PI who could not be happy if, right, suddenly you've acquired some $1,000s of data and, oh gosh, my experimental design was bad. We have to restart, which might or might not have happened to the speaker. I know there's somebody watching this remotely who's thinking, yep. In my lab. All right. So what I want to do now before finishing, and we're gonna, if I remember correctly, you're actually gonna see, and you will have a practical about this tomorrow that we're gonna do together, and you will have all the scripts to do this and bring it home with you. But it's going over the idea of efficiency. Now, if you can think of efficiency kind of as a number that captures the relative ability of a design to detect an effect of interest, right? So this is sort of a judgment on how strong the experimental design you've created is. And quite frankly, given that most of you do have MATLAB on some cluster that you have at your own university, and if you don't have MATLAB, Octave works just as well, and it's free. There's no excuse for not looking at this before you ever put anybody in the MRI machine, right? So hopefully tomorrow, as you try this, you'll kind of get a flavor on how to do it, bring home these scripts, and use them to your advantage. Let's put it this way. Let's say that we're interested in the difference in task A, task B, and their difference, right? Something like that. Whatever it may be, faces, houses, algebra, language, something like that. Now, if you think of what your t-test ends up being, is really the estimate of, let's say, the difference between A and B over its variability, right? So that's essentially what you're doing. Now, efficiency is proportional to that. In fact, given a certain contrast, C, and a certain design matrix, the ordering of your events, efficiency is 1 over the variance of what you're looking at, right? This defines efficiency. Now, let me break this down a little bit, right? So if you go through, right, if you use the standard notation for a GLM, you might end up with something like 1 over the estimate of the variance, contrast, transpose your betas. But really what I want to show is this. That was anticlimactic. This, right? So this is the expression, again, if you like GLM, if you like matrices, you might be familiar with this. But here's what's so interesting about this. So the first term is noise, all right? You can't do anything about this, right? So when you're calculating the efficiency of your design, well, noise will be in there. You can't do anything about it. Or rather, you can do something about it, and it's in the pre-processing. It's not in your experimental design. Everything else that is in here is actually something that you can decide before you ever put anybody in the MRI machine. For example, CT is a transpose of your contrast of interest. Who decides the contrasts of interest? XT, all right, X transpose X. What is that? That is the design matrix. Who decides the design matrix? Right. And of course, the last C, you decide that one too. So before you ever put anybody in the MRI machine, you can use efficiency to your advantage to calculate how good your experiment is, right? Or at least, you know, how much bang for your buck you should expect to get out of this one particular experimental design you've created. The reason for this is that when you sit down at your desk and come up with an experimental design, there's so many forks that you could take. And what are you going to base those decisions on? Some things you can decide, psychological factors, right? Those you can decide. But then think, should I randomize, not randomize? Should I block? Should I do event-related designs? How many trials do I need for the event-related design to get something comparable to my block? Do I have that much time to do event-related design? Right? Can I sort of have an experiment that is so long that will have all the events that I need to approximate the power of, or the efficiency rather, of a block design? These are all decisions that you're pretty much doing sitting at your own desk. Probably you've taken these decisions in the past by looking at whatever was done previously in your own lab or previously in the literature that you happen to inhabit, right? And this is terrible. Given how easy it is to look at these things, there's no excuse for not coming up with 3 or 4 different designs and then just put them through the simple scripts that you will get here tomorrow. Very simple to use. Let me give you some examples, sort of how this translates into practice. Let's say our X matrix is, again, task A, task B, the mean, something of that sort. Now, what are my contrasts of interest? So the C matrix, well, direct comparison, so A minus B. And then I really also want to see each task versus its baseline, just to get sort of a view of overall what does it take to see faces and houses. So 1, 0, 0, 0, 1, 0. Right? These together make my contrast matrix. And here are the questions. Should I randomize, not randomize? Event-related or block? Should I use rest periods in between blocks, or can I do away with the rest periods? If I could do away with the rest periods, I can jump back way more trials in there. Right? Again, you're usually sitting at your own desk, pondering or potentially career making. No, it's not true. But over what could be very important factors. Right? So here we go. If you're not familiar with this display, just because the software you use doesn't use exactly this display, on the sort of along the vertical of this display, I'm showing each condition. So condition A, condition B, mean, and the intensity of the bar. If you take those, I usually show this sideways, right? This is sort of what I show. It's the same thing. You have to imagine that the color is sort of the task coming out towards you. Right? So, for example, red means actually this side is easier. Task on, task off, task on, task off, task on, task off. Right? And in a randomized, of course, maybe here you have many tasks. Here you only have one. Here you have many back-to-back. Here there must be 3 or 4 back-to-back. That's why the intensity is like this. So which of the two should I use? Well, very simple. Let's look at efficiency. The overall efficiency of my fixed design overall, so given my 3 contrasts, and giving the experimental design, which is this on, off, and the interleaved off, on. Given this particular experimental design, the efficiency is 0.31. Great. Is that a good efficiency? Well, it's not a number in the sense, it's not a quantitative number, it's a relative number. So you can only tell compared to a different experimental design. By the way, you can also look at individual contrast. So my 1 minus 1 contrast has an efficiency of 1.35, and my versus baseline contrast have these 2 efficiencies. Well, let's compare that to the numbers I get from my randomized approach. And here we go. Now my overall efficiency is 1.32. Right? You don't do any stats on this. You just really look at the difference, and it's a pretty good difference. What is interesting is that not only my task versus baseline went up, sorry, task A versus task B, but really, what really got boosted now is my task A versus baseline and task B versus baseline. So now you know that actually this design is way better, really across the board. But now, okay, so this is a good design, and I'm keeping down here the numbers you saw a second ago. But how about if I compare that to a block design? Assuming that the psychological processes of interest are amenable to being blocked, how well does this block design work? Right, so, 30 seconds on, break, 30 seconds on, break, 30 seconds on, right, for the two conditions. Well, here we go. Gosh, 4.80 overall efficiency, and really, again, across the board, I'm just getting a massive increase in the efficiency. Right? Of course, you knew that, right? I told you at the very beginning, block design is way better if it fits your cognitive process of interest, which it might or might not. And now, yet another question. Is it the same? So I think up here, oh no, sorry. Can I just do away? Here I had all this waste of time, right? Can I do away with those breaks and just have task A, boom, task B, task A, task B, task A, task B? Somebody has an intuition for that? Well, let's see. I'm sorry? You can't space them? The contrast against baseline dies off. Why? There's no baseline. So if all I cared about were condition A versus condition B, that'd be great. In fact, I've done this in the past. I've just done away with breaks. I just need condition A versus condition B. I don't care about the against baseline. There was some good reasons for doing that. And indeed, if you look at the down here, if you look at the no rest, so the A, sort of A minus B, they work the same, because overall, you're spending the same amount of time under A and the same amount of time under B. What is changing is A, the overall length of the run, right? You can see here 160 versus 80. Of course, because I pretty much took out half of the time, which was just wasted staring at a fixation screen. But now I lost completely the ability to do condition A versus baseline and condition B versus baseline. So again, if you don't care about that, then by all means, not only still do 160 volumes, but acquire twice as much of this, right? But see, these are the questions that you can ask yourself without ever going to the MRI machine, without ever spending a single dime on fMRI time. Right? Way better than discovering this after the fact. And this works great. What I'm going to show you tomorrow, works great for detecting these kind of things, and also for detecting problems in your design matrix, which I'm going to get back when we talk about the GLM. So let me just sort of bring this together with kind of a good practices summary. Of course, keep in mind, I'm going to say some general remarks. Your specific experiment might have good reasons for differing from what I'm going to say. For one, look, bigger is better. More trials, more TRs, more subjects, right? Better. Always counterbalance, randomize, pseudo-randomize, whatever you can do, right? And then ask yourself many questions. What's the best design for your cognitive process of interest? And this, you're really introspecting, right? You're really thinking over, you're looking at the previous literature. In terms of turning your question into an MRI task, there you're introspecting. But in terms, right, of then designing the actual thing, right? So what's the best design for your task? Here you can do a lot, right? And then once you have different designs in mind, what's the psychological factors that might be at play? If I block this, is it going to work? Is it going to lead to strategies? Is it not going to lead to strategies? Do I need to do a jitter randomized to minimize, do I need to have single events in order to prevent mindsets and stuff like that? And of course, what comparisons interest you? And above all, maximize your efficiency, simulate. Go home, spend a little time looking at this, see which approach is best. And then at least you're going into your experiment with, a little more confidence than you would if you never looked at that. And finally, a note on humanity, be considerate. For how long you think you can keep someone, even your over-caffeinated 20-year-old undergrad, inside an MRI machine and get good data, right? And I think I'll leave it at that. And questions? Or take a breath first, I'll do the same. And then, so let's see if there's any questions coming up. Yeah, yeah, and tomorrow I have to speak for more. Microphone's down there. Can you get it in front here?
The last example, yes. So if you still keep 160 degree of freedom, would your overall efficiency improve or no?
Again, this is a first level. So my degrees of freedom, and again, my degrees of freedom are not about the estimation, but are about the inference. And here, I haven't yet gotten into the inference stage, which is where the degrees of freedom would become particularly relevant. But again, usually, not to say always, but usually, you don't get too touchy about losing degrees of freedom at this stage. You got so many, and it's not where you will do the inference. You know, always better to have as much as possible, but not as big a concern at this level.
But, I mean, so like, let's say if you're removing rest block, right? Would you still suggest scanning 160 versus?
Well, no, I mean, well, here, for the one comparison that I can do, I have exactly the same efficiency, right? So that tells you that at this stage, it's not that big a deal. Because here, the number of TRs during task A and task B are exactly didn't change. The volumes under each condition didn't change. I paid it here and here. Yeah. Give it a second. There you go.
One thing that I guess one could do, and I wonder if you could comment on that, is to have, so imagine you have four conditions, not just two. You can have blocks of condition 1, 2, 3, 4, and then rest.
Sure.
So, which would again give you more space, and I guess what you're asking is, if you do 160 volumes, you're gonna get more data out. So that's obviously good. I mean, more is better.
Yeah.
So if you do that,
But it's data that is irrelevant to what I'm doing, so it's actually a waste of time. Right? Well, if you really wanted to keep the 160, I would double up on the task A, B, A, B, A, B, and then do another 80 of A, B, A, B, A, B, and then you're really hammering it.
but do you think there's obviously one could run this optimization thing, but is it better to have? So imagine you have these four conditions, you do 4 blocks, and then you do rest.
Sure.
I imagine you get both things out of it. Possibility of running against baseline, but also more time for your.
Yeah, as opposed to 1 baseline, 2 baseline, 3 baseline. Yeah, absolutely. You can certainly do that. You'd have to run it through this to get the exact number. But I do not see a huge problem with that as long as everything's counterbalanced and this and that, and you don't get psychological effects, et cetera, et cetera, et cetera. Yeah. So essentially what you're doing is you're inserting blanks here and there. Yep.
Is it possible to do this type of estimation if you have 2 groups and you expect a different activation in one group for, you know, a condition versus another group?
No, because this is completely agnostic to the data. This is purely, you can see it this way. This is just how well am I setting up my design. This doesn't know anything about the differences between groups or real data. This is just, am I setting up for the best possible design? Very important, but. Yeah, back all the way. We need to leave a microphone with you.
I'm sorry.
No, this is great. I couldn't be happier over seeing your questions.
So if we think about group level designs,
Yeah.
They also involve like group A blocks versus group B blocks
Mhm.
that you do. So the tools that you are specifying, can it be used then to?
Yeah, so the way I've set it up, for example, and the way in which people usually have used this in the past, is on the single subject. I see nothing wrong with coming up with a way that, because it's really the same, right? If you think about it, all that you're doing at the group level, if you're doing the standard two-level hierarchical approach, is that you're going to have an X matrix that specifies patients versus controls, and a contrast that specifies what you're doing about it. Right? So in that sense, you sure can use the same approach. It also is true that usually at that level, all you're doing is A minus B or something of that sort. But you could use the exact same framework to look at something like that. Just currently, it's just set up to look at time series, and it looks at how well you're recovering. If you knew what was the real beta, the real parameter, it really tells you how well you're going to recover it. You can think of it that way. If you did, 1,000 simulations with noise. But yeah. Alrighty.
Give this guy a pass. Recovery is close.
Yeah, before we start talking about the GLM.
Thank you so much for that. And I think that's it for today. Am I right?
I think it is, yes.
Very good. Thanks everybody for being here. We'll start tomorrow morning. Lectures will start at 9. And you guys should settle in a bit. And what else do I have to tell you? I have a quick question. I have the opportunity, if people are starting to feel very peckish in the afternoon, of putting some light snacks in back. Are people feeling like they cannot survive without that, or I should try, or any feedback with that? Who would like